Here we'll look at visualizing our data using a histogram so we can see the frequency of when certain values appear in our data set. So what a histogram does, it shows the frequency that our data points appear within certain bins. Now what a bin is, at least the way we're going to use the histogram in this course, is we take our whole range of data. So let's say we have data points that have the minimum of our data is -5, the maximum of our data is +5. What we do is we take that range and we break it up into a certain number of bins. By default, it uses 10 bins. So what we would do is we would see how many of the data points lie between, if we had 10 bins, -5 and -4, how many of the fall between -4 and -3, -3, -2, -2, -1, and so on, into each of those bins. Now the bigger our range is, then the bigger each bin is going to be. So if our data went from 0 to 100 and we wanted to split into 10 bins, then each bin would be a range of 10 numbers. And we can choose how many bins to put in, but let's look at just the default method we can use histogram. So using that same data set as before, I have that vector A of 100 data points. I'm just going to use the default hist command to do this and see what it produces. So we see here we have a visualization of our data. The x-axis is going to be the value, and these again are in bins. The default doesn't give us very nice bin edges here. We'll work on that in a moment. And then the y-axis is the frequency, or how many times a value between the two endpoints of the bin appeared in our data set. So let me just put the grid on so we can see a little bit easier here. So we see here that between -3 and, we don't have this exact value, but about -2.5, one value laid in that range. 4 laid between about -2 and -2.5. 6 values between -1.5 and -2, etc. So we see that kind of the most appeared near the mean of our data set, and then near what we call the tails, or the endpoints, fewer and fewer of those data points appeared. And this is going to be important when we talk about normality in a little bit. So like I said, the default, just using hist, doesn't give us anything that great to look at or to analyze, but at least gives us a rough idea. So the second argument we can give hist is the number of bins to use. Like I said, the default is 10 bins for the plot. But if I put in here more bins, we can see we get a little bit more detail, because now each bin is smaller. So now the range, if we use 20 bins, is between, say, -3 and -2.75, -2.75 and -2.5, etc., all the way down. So it gives us more, what I'll call resolution here. And if you use fewer bins, it does kind of change this picture, because now each bin encompasses a larger range. So we see we had the same data. I had 3 different numbers of bins that I was using, and the visualization looks quite different. So how do we know how many bins to use? There's no real answer to that, but there's a couple of kind of rules of thumb or best practices for choosing how many bins to use. So the first we'll look at is Sturgis's rule, and there's a link to this on the website if you want to look a little bit more about it. But what Sturgis's rule says is that the number of bins we should use is going the ceiling of the 2 log of the number of elements plus 1. And that's the best number of bins to use according to that rule. So what we want is to use the ceiling function. I'll explain it in a minute. And then we can use log 2 of the number of elements we have. It's not the elements themselves, but in this case, it'd be log 2 of 100 plus 1. Okay, so first let me kind of work from the inside out. Length of A, we already know for this set is 100. If I take log 2 of 100, I get 6.64, and I'm going to add 1 to that. So the number inside here is 7.6. Now when we break it into bins, we can only have an integer number of bins, since they're all going to be equally spaced across our range. And right now we have 7.64, which is clearly not an integer. What the ceiling function does, it's similar to rounding, except ceiling always rounds up. Or I should say, it always rounds to the larger positive integer to our number. So for a number like 7.64, it's going to round it up to 8. But let me look at ceil just a minute more. If I use standard rounding rules, 6.2 should round to 6, but using ceiling, it rounds up to 7. And why it's a little bit different than just rounding up, we want to be careful here. If I have like a negative number, negative 2.3, and I put the ceiling on this, I have negative 2 because it'll round to the larger integer. So negative 2 is larger than negative 3, or it's more positive than negative 3. And while I'm talking about ceiling, I can also talk about floor, which will do the opposite. If I have floor, it rounds to the smaller closest integer. So 6.3 rounds down, but it also will round down 6.9, also to 6. But if I have a negative number here, we see that the floor, the smaller closest integer, is actually negative 7, since it's more negative than negative 6. Alright, so that's enough on ceiling and floor, but that's what Sturgis's rule says. It suggests using that many bins, which I will call n. And again, for 100 data points, it recommends using only 8 bins, not the default 10. So now if I do the histogram with 8 bins, and I plot it, now it says that that is kind of the best picture to be looking at, according to Sturgis's rule. An alternate rule, instead of Sturgis's rule, is the Rice rule, and that's going to suggest that we use the ceiling of 2 times the cube root of the number of elements that we have. So in this case, that's the length of A is the number of elements we have, and we want to take the cube root, which is the same as raising it to the 1/3 power. Right, so again, if I look at the inside here, according to the Rice rule, that's 9.28. And if I take the ceiling of that, Rice rule actually for 100 agrees that we should have 10, which again is the default if we just use hist. So using the Rice rule, we have 10 equally sized bins between the minimum value in our set, which let's look here is a negative 3.02, and the maximum value in our set, which is 2.22. And going back to our figure, but we don't have exactly where these edges are that were being used here. So again, this is why using just hist, the default is not necessarily the best. But another way to use hist is that it can, instead of just plotting directly, it can give us the data that basically created that plot. So what I can do is save these 2 values, x and c, out of hist. If I rerun this now, we see it. If I do that, it doesn't actually plot anything, but it does return these values. So what it does in this x vector is it gives me the frequency that something was in the first bin, the second bin, the third bin, etc. And it gives me this vector c. And if I look at c, this actually gives me the center values of the bins. So it's not quite as good as seeing what the edges are, but this tells me that I have a bin centered at negative 2.76, a bin centered at negative 2.24, etc. I can figure out then how big where the edges of the bins are, because the edges are going to happen at really the average values of the bins, or of the centers of the bins. So if I look at, for example, the mean of the first value of C and the second value of C, that tells me where the edge of that first bin is. So the first bin, its right edge is at negative 2.5. But we can see it that when we start to plot this, it does give us a little bit more detail. And really we're just going to worry about the picture mostly for this course that it made. So what I can do from here is it didn't make me a plot, but I can make my own using bar, which makes a bar chart. In this case, I want my x values to be the centers of the bars, and then x to be the frequency. And let me hide that for a minute. So we see it makes a pretty similar plot to what we saw, but by default, it's trying to put these integer values in here for my tick marks. But the picture looks the same as if I just used hist, although I probably want to tighten up the axes. And also, now I have the option of using different colors, so I'll just use black bars for this. So we have our histogram here, again using 10 bins for right now because I'm using the Rice rule, which suggested using 10 bins. But again, we see it doesn't actually show us the centers of these bins, it just has these now 0.5 apart indicators, but that's not as helpful as looking at where the center of each bin is located. Now, fortunately, putting that in is not as easy as it should be, as many other things in Matlab are. I have to use kind of this compound function here and use this code here. Alright, so what this is doing is it's setting what we call a handle. Don't worry too much about what it's doing here, but it's setting a handle to h, which is basically a variable that is figure number 1, and then I'm saying set the x ticks in this figure to the values in C, and those were the bin centers. And we see what the difference is when it's plots. So now, again, making it a little bit bigger, setting the grid on so we can see it a little bit nicer. Now I specified where to put tick marks here, and now we see that the numbers are the bin centers for each of those 10 bins. If I go back and use Sturgis rule rather than Rice rule, I see this now works, and I only have those 8 bins. So again, for the bin centered at negative 0.0712, I had 30 values that fell between the left edge of that bin and the right edge of that bin. And then going down to the bottom here, I have about 2 that fell between the left end of this bin and the right end of this bin. Now by default, this tells me the frequency, or actually how many total values fell into a bin. But what's often more useful is, instead of the histogram, is to use a relative frequency histogram, which is going to tell me, like, as a percentage of all my data, how many fell in specific bins. So to do this, it's quite simple. I have, again, that vector x that tells me the frequency. So if I want to know the percentage, I just have to divide each of them by the total number of data points that I had. So when I make this bar, I'll demonstrate it down here, all I have to do is x divided by the length of x, and now everything is converted into a percentage. Oh, sorry, I didn't want the length of x, I wanted the sum of x, because that's the total number I had. And I should find that the sum of x is 100 because I had 100 data points, and it is. So again, looking back at x over sum of x, this tells me that 2% of the data fell in the first bin, 4 in the second bin, 11 in the third, 17, 30, 18, 13, and 5%. If I go to this, bring this back up one more time, this is my normal or frequency histogram. For the relative frequency histogram, I divide by the sum of x, the total number of data points. And now if I replot this, now I see that my y scale has changed. So now I see that, again, in that center bin, I have 30% of my data, etc., as it kind of dwindles down. Now, a nice thing about the normalized frequency histogram is now I can add areas together to see what percentage of data falls below certain points. This works with quantiles, really, in a very similar way. So I can see that if I add the areas, so let's say of the first 2, let's just see what numerically that's going to be. So that's going to be 6% of the data. So if I add the area of this plus the area of this, I get 6% of my data. 0.02 plus 0.04, 6%. So if I go a quantile of A, and I look, what is the 6th percentile, I get negative 1.8. So 6% of the data lies below negative 1.8, and that should actually be this edge here, because I see everything to the left of that, everything lower than that is 6% of my data. And then if I look again up here, if I look at those first 3 bins, that's going to be 17% of my data. So if I look at the 17th percentile, that's negative 1.047, and that corresponds to this right edge here, because again, everything to the left of that is below it, and that is 17%. If I add up the area of all 8 of my bins, I have to get to 100% for the normalized frequency histogram.